Okay. So the stuff that I'm going to show you today with the conservation of energy, like I said, this is going to be nothing new. You've seen this all last year. We're just condensing it all down a little bit. And that's why we have both energy and momentum all in one unit. So it's like pretty squished, but it's all stuff you've seen. So does anyone remember the word explanation of conservation of energy? Yeah? Yeah. Yeah, exactly. So energy cannot be created, nor can it be destroyed. It can only be transformed into another form. So transformed or changed from one form to another. So the theory that energy has been the same since the beginning of the universe, it just gets transferred from one to another. Therefore, if we have only conservative forces, do you know what conservative forces are? So a conservative force is a force that you can gain back the energy lost. So something, for instance, like if I hold my water bottle here, if I lower it, I change its energy, but I can gain that energy back by just lifting it up again. As opposed to something like friction, where if I were to slide my hand across my hand, I lose energy due to friction. If I try to reverse it, I don't gain the energy back. I've lost it again. So conservative just means you can gain it back by doing the reverse motion. So if only conservative forces act in the system, the total change in energy is always zero, meaning I don't have a change in energy. Looking at the whole system, yes, individual things might change. I might go from some potential to zero, but that energy gets transferred into something, either kinetic or heat, as we'll see later. So total initial energy equals total final energy. This is what you saw last year. So this is EPI plus EKI equals EPF plus EKF. If there's something that I'm saying it's pretty easy to remember, but you don't remember it, please remind me, because I taught this like just last week to my grade 11. So for me, it's fresh. I know for you guys, it's not. So if I were to take each of these individually and plug in the number, or not the numbers, the actual equation. So potential energy, this is mgh. So I have mghi plus a half mvi squared equals mghf plus a half mvf squared. So this is the total conservation of energy equation. We're going to slightly change it a little later, but this is what we've got so far. So whatever energy I start with, I have to finish with. And as we said, the total change in energy is zero. So this means my change in kinetic energy plus my change in potential energy must be zero, since that's the energy we're dealing with. So if I just solve this for change in EK, this equals negative change in EP. And this makes sense, right? As one of them increases, so if my kinetic energy goes up, my potential energy has to go down, and vice versa. So as one goes up, the other goes down. Yeah, so if we have only conservative forces acting, that means you have a closed system. Or in a closed system, that just means we have no outside energy coming in or coming out, is all that means. So it's similar. So let's try an example with this. So if I've got a roller coaster, it tells you what the first peak is, 55 meters above the ground. We've got a car that's starting from rest, and there's another hill. We want to know how fast is it moving on this other hill. Classic physics example for conservation of energy. So here's my initial point. We're told this is 55 meters above the ground. We know at the second hill, this is 30 meters. Not really drawn to scale. And I want to know, what is my speed over here? And you're told the mass, told the initial velocity. So to do this, I just use my equation. And if you remember, there's something special that I can do in terms of potential energy. Do you remember what it is? Because potential energy is relative. Yeah. So I can say my potential energy is relative to the ground and use these two heights, which is fine. That still works. But if we want to be smart about this, we can make a line here and say at this line, my potential energy is 0. Because it's relative. I can pick whatever point I want. The reason why this is helpful is now my potential energy here is 0. But the trick with this is now this height changes. Instead of it being 55, now it's 25. So that's the only part that changes. And algebraically, you can see why both of these work no matter what. I'm not going to show it now, but trust me, it works. So we go back to this equation that we have. And first, let's check, is there anything I can cancel out because it's 0 at this point? EPF, yeah, because we just said that that's 0. What else? EKI, yeah, because I'm starting at rest. So if I'm at rest, there's no kinetic energy initial. So this makes it a lot easier. Now I'm just left with EPI equals EKF. Not too bad. So MGHI equals a half MVF squared. Now at this point, you can plug in the numbers and solve it. But I can do a little bit of simplifying here. Both sides have a mass. I can just cancel them out. If you don't recognize that, that's okay. But sometimes they won't give you the mass. So you could put the masses in there. You'd get the same answer. Wouldn't be too difficult. But this just makes your life a tad bit easier. Then plug in your numbers and solve. So if you did this, you'd get a final velocity of 22.1. Or final speed of this, since we don't need direction. Any questions with that? Okay, so if it wasn't, that's a good question. So if I didn't cancel out EPF, we can look at how that would change this expression. So over here I'd have plus MGHF. And what I would need to do is I would need to take this and minus it on this side. So I'd have GHI minus GHF. Factor out the G. I get HI minus HF. And notice 55 minus 30, I would get back the 25 that I have here. So that's why it's a relative, because it doesn't matter what I pick. I just need the difference between those two to really solve it. So that's algebraically how you know it doesn't really matter. It'll still get you the same thing. So that's really how easy it was last year. Right? When you go back and look at the stuff you took before, you realize it's much, much easier. Although we expanded on this a little bit. We talked about non-conservative forces. So we talked about friction. And we talked about heat as well. So I think this part wasn't always taught in grade 11. That's why this isn't anything new. So essentially, what all of this is saying is, as you have an object that's moving, if you've got friction, you're going to lose energy due to heat. So friction causes heat. If you rub your hands together, they create heat. So when you have something like this, where you've got a wooden block that's moving down an incline, there's going to be some friction that's involved. So if we're looking at up top, there's an energy initial, and down at the bottom, there's an energy final. You're going to lose energy in this system. So if we look at this, what does this say? How would the block's kinetic energy at the bottom compare to the potential energy at the top? So if we were to look at energy potential initial and energy kinetic final, because it gets converted from potential to kinetic, is EPI bigger, smaller, or the same? They're the same, right? That's what the conservation of energy says. In a closed system, okay. Great. So we've got all three options. Jana, you're the tie-breaking vote. Okay. So we've got a mix of answers. This is good. So let's think about this. So on the previous page, we said energy initial equals energy final. And that's if I've got only conservative forces. The problem is, now I've got friction. Friction is not conservative. So the energy that I have initial, yes, some of it gets converted into the final energy of the block. However, part of it also goes to heat, which I think, Haneen, that's what you said, right? So my EPI, which is the initial energy here, part of it gets converted into kinetic energy, but part of it's lost as heat. So it goes like this. The initial energy is going to be slightly higher than the final energy of the block. So we haven't destroyed any energy. We've just taken some of this potential and converted it into heat. So I haven't lost it. It's still there. And that's why we consider this a closed system, because we're going to include heat inside of this closed system. You can imagine like this is all in a box, and I'm containing the heat within it. So I still have it. It hasn't disappeared. So we have this because we have some EPI gets converted into heat. So that's where it goes. Again, not destroyed, just converted. Any questions on this? Okay. So we need to make a slight adjustment to our equation. But first, what does this say? The fact that the amount of energy in the block decreases as it slides down the ramp doesn't change the fact that the total energy, yeah, this is just what I said. The total energy in the system is constant, and we just need to change this equation slightly. So, which one did I put? I put this one. Okay. So we talked about EPI plus EKI equals EPF plus EKF. And now we're going to add on to this heat. So some of this initial energy can still be converted into heat. And this way, the total energy is going to be conserved. I'm just also including heat in that. Which also changes our other equation here. So change in kinetic energy plus change in our potential energy plus the change in the change in heat. All of this must equal 0. And notice with this, my change in heat always has to be greater than or equal to 0. So I cannot have a negative change in heat. That would mean I would need to take heat from outside the system and pour that back into energy into an object, which we cannot do.
Why is it plus changing? Why is it plus like heat doesn't have those two components and final energy?
You mean in here?
Yeah, here it is like an initial and the final.
Right. That's a good question. So why is this not initial or final heat? Or why do I not have an initial heat here? So in our system, like I said, you cannot put heat from outside back into an object and create a different kind of energy. So I'm never going to have an initial initial heat and then a final heat that's 0. So it just has to do with, I can only get the heat out of the system, I can't put that heat back in. Yeah, essentially the heat initial is always 0, yeah. And that's why my change in heat can only be positive. I can never have that be negative. Okay, so let's try another example. So we've got a wooden block. It's pushed down a ramp with some velocity. At the bottom of the ramp, you're told what the speed is. We want to know how much thermal energy is generated due to friction. So here's our system. This is what we're dealing with. So let's try this out. We're dealing with conservation of energy. So start off with this big long equation. So always put heat in there. I would suggest that for your questions. Even if you know there's no heat, you can just cancel it out like we've canceled out the other stuff. But it's good to have it because people often forget that there is heat loss. So in this case, what can I cancel out? Or is there anything I can cancel out? EPF, yeah, we can set our 0 point at the bottom. Did we start at rest? No, so I cannot just cancel that one out. And kinetic energy isn't relative. So I can't just say at the top it's 0 and it's relative to that. It won't work. So this is the only thing we can cancel out. The rest we need to solve for. So plugging this in, we got mghi plus a half mvi squared equals a half mvf squared plus eh. So here's the question. Can I cancel out mass again?
No.
No, why not?
Because the equation of the energy is
Yeah. So this one doesn't have a mass. Technically, if I wanted to write it as, what is it, mc delta t, like we learned last year, I could get a mass from this, but we're asked what is the thermal energy. So I'm actually solving for EH. So therefore I cannot cancel out the masses, I just need to solve for this. So plug in all the numbers. What do we got? We got mass, we got 9.8. Initial height. So this is my distance I'm using. Not the 3.5. The 3.5 doesn't matter in this. And then solve for EH. I'm not going to plug in all the numbers for this. If you want to see that, you can see the completed notes and double check it. I'm just going to tell you that this is 22.9 joules. Because at this point, I think you can get the rest of it. So there's the heat. Now we want to figure out what's the force of friction. So in the past, we would take this, we'd go, what's mu Fn? Then you'd have to figure out what's the perpendicular component of gravity, figure out the normal force, use the normal force, solve for that. Now it's a lot easier because we have change in EH is equal to force of friction times distance. I have my change in heat. I just solved for it. What's the distance that this heat or the friction force is being applied over? 3.5. So here's where the number comes in. This comes in for the distance that we're using down here. And then we just solve it. So we got 22.9 equals force of friction times, or this is 3.5, right? Oops. Calculate that, 6.5. Any questions with this? So really the only thing that's changing from last year is maybe this equation. I don't think I showed you this specifically, that heat is force times distance. That's something that's slightly different, but everything else is the same. So that is conservation of energy.